All right. So I said I would have those Excel assignments graded, and I didn't quite make it through everyone's. I was working on those this afternoon. But those grades should be up there by the time I leave tonight. I'll put the answer key up for that as well. I'll also be putting up the next Connect assignment, which the due date will be quite a ways down the road. We've got kind of Thanksgiving break in between. But as we cover material today and on Monday, you should start to be able to chip away at the majority of those problems. So I want to kind of get it out there so that as we cover through things, if you've got some time before break, Thanksgiving break might be a good idea to start working on that. Okay. I'll also put up the next Excel assignment. I should have that posted before I leave tonight as well. It'll be kind of similar to what I was going back and forth. I was thinking about doing some asking you questions about stuff that we'll be kind of covering today. But I think I'll instead make it a little bit easier and just kind of do the one population hypothesis testing Excel examples we worked through on Monday. So it'll look very similar to what we did on Monday, kind of using that as a template. Yeah, I think that should cover all the housekeeping stuff. Any questions for me before we kind of jump into things here today? Yeah.
Did you post what you did on Excel? Yeah. Like what we did?
Oh, no, I'll put that. I'll make sure that when I put up the next assignment, I'll put the in class or with all the completed stuff in there as well. Yep. In fact, it might already be up there. I might not just called it in class. I might have just called it. Let me see. Let's see here. Yeah, so this one that doesn't say blank, that actually it's not going to be an exact mirror because I'm sure I like type something in with a lowercase, but that's basically what we did. But I'll upload the one in class too, just so you have that. Thanks for asking. That's a good question. All right, so we've been doing 3 different types of examples when it comes to confidence intervals and hypothesis testing. So all of them were for one population where I was looking at the sample mean or the sample proportion. Sometimes when I had the sample mean, I had a known population variance. Sometimes I just had a sample variance. So when we only have a sample variance, we had to use the student t distribution. But other than that, the test statistic equation looks a little bit different, but the steps are kind of very similar. Right? You got left, right, two-tailed test for each type of example. So now we're going to be doing the exact same thing, but instead of just looking at one population, we're going to be comparing 2, right? So comparing 2 groups to each other. Now, the principles of what we're doing with confidence intervals and hypothesis testing will not change at all. The test statistics and the equation to calculate the confidence interval might have a few more moving parts, but conceptually, we're really doing the same thing. It's just that we're comparing 2 populations, we can make some more interesting statements. So, kind of the 3 situations that we're going to have is we're going to compare sample means when we know the population variances, compare sample proportions from 2 different groups, compare sample means when we only have sample variances, and then the same kind of settings when we have for confidence intervals and hypothesis testing, right? Those same 3 types of examples. It's just now, and I forgot, we won't cover this probably until after Thanksgiving break, but we'll do some matched pair stuff as well, okay? So some kind of the examples we should be thinking about, and we'll kind of work through all of these. But let's say I had econ and theater major starting salaries, right? And I want to know, is there with 95% confidence, can I build this interval for where the true difference in these 2 different major starting salaries is, right? So I want to create a range of values where I can tell you that econ majors make somewhere in between this amount more than the theater majors. Or maybe I've got a survey done in 2 different time periods, and I want to know, in this one, I think it was what, the Affordable Health Care Act. So over time, right, going from 2011 to 2010 to 2011, did views become more favorable of this act, right, or less favorable? Can I build, confidence interval for what the true change in opinion was, or the true change in the proportion of people who are in support of this? Or maybe I've got texters and non-texters, and I say, their response times is the difference between the response time of people who are texting while driving versus not texting. Is there any difference there? And if there is, what are the possible values that difference could be? These are going to be kind of the general setups. So let's think about the case where we walk before we run, and we're looking at sample means, but we somehow know the population variances. Once again, maybe a little bit hokey at first, but right, understanding this, then once we move to sample variances, it'll be a little bit easier. So if I take a sample from my first group, so maybe this is like my econ majors, right? They have some true population mean and some true population variance. I draw some sample size. I could then know what the distribution of those sample means look like. Okay. I could then take another sample from my theater majors, right? I know those sample means that I would see from my theater majors will be centered around whatever the true population mean is for theater major starting salaries, and it has its own population variance. Okay. So here's where, and hopefully these equations will make a little more sense in just a second. So I'll kind of give you some support. I'm really not walking through the mathematical proof, but I think the intuition alone, I think this will kind of line up, right? So let's say this was kind of my group one, and here was kind of my second group, right? So if I'm thinking about the sample means that I could see from group one, they should be normally distributed around whatever that group's true population mean is. Same kind of thing for group two. Okay. So if I instead think about, well, I'm no longer interested in just the sample mean. I'm interested in the difference between these sample means. Right? So the difference between my first and second group, right? Or econ and theater majors. So you can kind of think about this. I don't usually write it like this, but you might see the notation here and on other places, right? I'm kind of finding like my sample difference, right? The difference between these two sample means. So what's going to be the most common difference value that I see? Well, if this is the most common sample mean I see from group one, this is the most common value I see from group two, whatever that difference is, that would be the most likely difference value that I see. And then here's the next most likely values I could see. So, maybe I see a slightly smaller difference, and then next most likely here, right? So it's going to look something like that. And then when I'm starting to talk about, well, what's the likelihood I see this sample mean from group one and this sample mean from group two, and I see this really huge difference that's somewhere over here. Well, it's almost zero at that point, right? So what's going to be true about the distribution of our difference in sample means, as long as we have sample sizes over 30 for both of our kind of samples, is that it will be normally distributed, and it will be normally distributed around that most likely value, which would just be whatever the true difference was between those two groups' population means. Now, I usually can't observe this, but I can walk through the mathematical proof. And like I said, it's kind of intuitively, right? Like this is the most likely difference, the next most likely, so on and so forth. Okay. So I've got this kind of normally distributed distribution for the difference in my sample means as well. And I know that they're centered around whatever that true difference is. So you can already imagine that a normal distribution, maybe we can kind of turn some of these difference values we see into these z values and then find the likelihood that we saw this difference or anything below it or anything above it. But the other thing that we need is not only like where is it centered or what is the mean of that difference in sample means, but we also need to know, well, what's the variance? So notice now I'm looking for the variance of the difference in my sample means. What ends up being true, once again, you could Google and walk through the mathematical proof. It's not that interesting and also difficult to understand. But you can prove mathematically that, and I think it's kind of intuitive, the variance of the difference in your sample means will just be the variance that exists from that first sample mean added to the variance that exists for that second sample mean. And then once we get to confidence interval hypothesis testing, we usually want standard deviations. So then we just take the square root of that. So to get the variance of the difference in sample means, we're just adding the variance of each sample mean together. And then if we wanted the standard deviation, we'll have to take the square root. Any questions over this idea before we keep moving here? Shouldn't be too bad, yeah. So if we think about then, how could I build a confidence interval? So I'll try to kind of relate this to what we've already done. But when we're doing this with one population, we said take the sample mean, add and subtract a certain number of standard deviation that gives us alpha over 2 on each side of our confidence interval. And then here, we just multiply by this, where this guy here represented that standard deviation of the statistic I was interested in. We're doing the same thing. We're looking at the difference in sample means. It's just now, instead of centering my confidence interval around just a sample mean, I'm now interested in the difference. So I'm going to center my confidence interval around whatever that difference I find is in my two samples. And then same kind of idea. If I know the population variances of the two groups, I'm going to go a certain number of standard deviations to the left and the right. That gives me alpha over 2 in each tail. It's just now, when I'm thinking about if that's the number of standard deviations the way I want to go, well, what is the standard deviation? That kind of comes from that last slide, right? Where we said the variance is just adding the variance of each group together and then taking the square root. So we're following the same format. We're looking at the statistic we're interested in, going a certain number of standard deviations to the left and the right to get our upper and lower bound, and then multiplying that by whatever the standard deviation is of the statistic we're interested in. So the steps are going to be exactly the same. Looking up those z-values exactly the same. It's just we got a few more moving parts now. You know, when it comes to kind of the exam, you'll have the formulas in front of you. You know, it's going to be kind of similar to what we're doing before. I'm building a confidence interval for the difference in sample means, and I know my population variances. All right. So these are going to be things that we're given: the sample means, the sample sizes, and the population variances, or we can calculate the sample means and sample sizes from data in practice. Really, the kind of key is just being able to look up that z-value. So nothing's really that much different. We've just got twice as many things to identify, right? Because you have 2 sample means, 2 variances, and 2 sample sizes. We still look up the z-value the same way, but then at that point, it's just a matter of getting everything to plug into our equations. Okay? And we'll start to do a little bit more with the interpretation of confidence intervals as opposed to kind of the computation there. And we still will compute them, but we'll talk a little bit more about kind of their significance. So let's say we had this set up where I've got econ and theater majors starting salaries. So I've got what? Econ majors 45,000, theaters 33 was my sample means. I somehow am given or know these population variances for the two groups, or it's 9 and 6,000. If I wanted to build a 95% confidence interval for the true difference between these two major starting salaries, what would that be? Well, start out, just a matter of plugging in what we found. So 45,000 minus 33,000, that's what we'll base our confidence interval around, because that difference in sample means is the best guess we have of where the true difference is between the population means. Kind of here, we'll come back. Here it's just a matter of, well, first group at a variance of 9,000, and I had what, 40 econ majors. Second group, variance of 6,000, and I had 50 of them. So this will kind of highlight even more how breaking these down into steps can help. Like, I can do this all at one time, or I can like get this entered into my calculator, just have one number. I can do this math, so I just have one number, and that makes the equation that I'm entering into my calculator a little bit easier. You don't have to. You can do it all on one line if you want to. But then the only other thing we have to do is look up that z-value. So if I want the 95% confidence interval alpha, 95% confidence interval. Yeah, alpha is just the percent outside the interval in decimal form. So 5% outside, alpha is 0.05. But remember, I'm trying to find the number of standard deviations to the left and the right I need to go, so that I have alpha total outside of my interval, or alpha over 2 on each side. Okay. So here, instead of looking up 0.05 in my standard normal table, divide that by 2 and look up 0.025. Okay. So once again, I think I kind of we looked at this last class, but there's multiple ways we could do this, right? So I could just go to that Z table, say I want the area of 0.025. What's the value? Or wait, is that what it was? Yeah, 0.025. I can find that exact value. The Z value that corresponds to that is negative 1.96. Hopefully we're starting to get used to seeing these same values pop up over and over again. Excuse me. That was the last thing I needed. Okay. So now it's a matter of getting everything plugged in. Now, another way I could have done that, instead of hunting for that 0.025 in the middle, I said, I think I told you this last class, I can use that last row as kind of a shortcut, right, from that student T table, because the last row is basically telling me my comparison values, what I would have found from a standard normal. So I go up here, I wanted 0.025 in the tail, scroll down, sure enough, 1.96, okay? We did go over that last time. I got a couple seconds, so I want to make sure if I'm saying that, if I ever say something, you're like, no, we didn't do that. But I'm going to say, I'm pretty sure we did that. So really the steps, I mean, it should look pretty similar to what we're doing before. I just have a few more moving parts. Now, one thing we could think about if I was working through a problem like this, and let's say, I don't know, I was on the exam and, have possible answers. What value is going to be exactly in the middle of this confidence interval? Close, yeah, right? Whatever that sample difference I found was. So sometimes, like, that's why I said kind of breaking this down to steps, and I kind of help you think about, yeah, my confidence interval is centered around this difference, but what is that difference? 12,000, right? And then from there, it's just a matter of computing this, right? So I've got everything that I was given. I looked up that Z value. Now it's just a matter of getting all those values plugged into our equation. We subtract that margin of error to get our lower bound. We'll then add it to get our upper bound. Okay. Any questions on that before we keep going here? So I want to start thinking about how do we interpret these confidence intervals. This one's pretty interesting in that it's just really, really small. So here I've got what, 11,964 and 12,000 is it 46, 56, 36. So what I can say with 95% confidence here is that the true difference between these major starting salaries is somewhere in this range. These are only positive values. So with 95% confidence, if I constructed this so that it was econ minus theater major starting salaries, if I only have positive values for what that true difference could be, what I can really say there is what? So if they're only positive values, that would imply that econ major starting salaries are higher. So if I find only positive values for this difference, I know that that first group has a higher mean than the second group. Let's say I only found, I don't know, negative values for my confidence interval. Well, if this is negative, the only way that's true is if theater majors are making a higher salary. Right? So if I only have positive values, I can say group one with that level of confidence has a higher mean. Right? Or the difference would be positive. If those difference values are only negative, what I can say with that level of confidence is that group two has to have a higher mean, or that the true difference is negative. Right? Now, the more interesting, or I guess not interesting, but maybe problematic, is let's say I found a confidence interval like this. What can I say there? Well, the true difference could be negative, which would imply theater majors make more. It could be positive, which would imply first group econ majors more, or the true difference could be 0, right? 0 is one of the values in that range. If the true difference was 0, what is that really telling me? That difference is 0. Yeah, they have to be the exact same value, right? The two means for the groups are exactly the same. So anytime 0 is in our confidence interval, we really can't say much. Because the true difference could be 0, right? I mean, I guess we can say that, right? We don't know if they're different from each other. But if I have only positive or only negative, I can then kind of give a sign to which group has a larger mean. At least at that level of confidence. Questions on that? Maybe another example, some different values. We kind of think about this. So let's say I gave you an example like this. I think maybe I'll let you guys kind of work through this one just to get some practice kind of working through these. Hopefully see any kind of problems that you might run into. Okay. So let's say I have a very similar setup, but I'm now instead of econ and theater majors comparing two states, Indiana to Ohio. So Indiana, I find a robbery rate of 109. Ohio, I find a robbery rate of 163. If I define this as the difference between Indiana minus Ohio, so Indiana is my first group. And I assume that my sample sizes for both 24, because I'm looking over the same 24-year time period for both groups. And I'm then given these known population variances of 175 and 497. What would that confidence interval be? So hopefully you got a way to look at those standard normal tables. If we're building the 95% confidence interval, you can look up that Z value. Although we're looking at the 95% confidence interval for the previous problem, so that might really help you kind of find what Z value you should be looking for there. So I'll give you guys a little bit of time to work on this, and we'll kind of talk through anything that was kind of difficult. When you talk to people around you, see if they know something you don't, you know something they. Another 30 seconds here. All right. If you haven't gotten an answer in, take your best guess here and we'll kind of go over it. It's 13 of us here. Thought I had 15. There we go. All right. I'm going to close it out. So this is how I would kind of break this one down, or at least start thinking about it. So I've got the equation up there already. I'm thinking about what is my confidence interval going to be based around? Well, no longer are these my sample mean values. But I found what? 109 minus 163. So it should be centered around that negative 54 sample difference I found. So right away I can rule out which of these? D, right? The sample difference I found isn't even in my confidence interval. Right? The whole point of the confidence interval, we're taking our sample evidence and building an interval around it to say, look, we know that this is the best guess of where the population mean is. But we know we might be a little off, so we're gonna kind of create this umbrella on either side of it to make sure like the true mean is somewhere in this range, or in this case, the true mean difference is somewhere in this range. From there, it's the 95% confidence interval. So alpha is still gonna be 0.5. When I look up half of alpha on each side, I'm gonna find that same value of 1.96. And then from there, it's just a matter of, well, what were my variances in my sample sizes? So the first group, 175 was the variance. I had 24 years. And then the second group is 497. And I had 24 years, or my sample size of 24 there. So it's really just a matter of kind of getting comfortable, kind of computing this, getting this entered into my calculator. Like I said, if it was me, I would probably find this separately. That way I've got one value here, one value here, and one value here, making just a little bit easier that, prevent me from making a mistake. So identify all the pieces that you're given, right? You've got that confidence interval formula in front of you. Figure out that Z value you give you alpha over 2 on each side. And then from there, it's a matter of getting those values plugged in. So you have what, negative 64.27 to negative 43.63. Any questions or difficulties or something with this one that anyone has? Okay with this? So I've got my range here. At the 95% level, just as a reminder, we defined this as the difference between Indiana and Ohio. So I've got what? Negative 64 to about negative 43 here. With 95% confidence, what could I say? Remember, these represent the property rates. So the only values in this range are negative, which would imply that my difference is less than 0. That is negative. What's the only way that's possible? If Ohio has higher robbery rates. So saying that this difference can only be negative, essentially what I'm saying is either one of two things, right? I can say that Indiana has lower robbery rates, or Ohio has higher robbery rates, right? There's different ways of saying the same thing. So you can kind of imagine, you can start to compare these differences across groups, might allow us to identify things like discrimination, or we're thinking about differences in the outcomes after two different countries took different policy decisions. Really, this could be applied to like a variety of different things, right? And it's really just using all the stuff that we've already talked about at this point. So let's look and see then how we might do hypothesis testing. Okay. So this is going to look a little bit different than we did before. I honestly think it's pretty much the same. The tougher part of it, if I had to say, is probably identifying the null and alternative becomes a little bit trickier than it was before. And that's only because the way we speak in English does not really line up with the way that we kind of write things all the time in mathematics. So before, as just kind of a reminder, when we were calculating test statistics, we took the sample mean we found and we subtracted the assumed true mean, right? Population mean. We then divided that by the standard deviation of our sample mean, which was just the square root of the variance over the sample size. We're going to keep the exact same format now, but we're looking at the statistic of the difference in sample means. So we're no longer looking at the sample mean, we're looking at the difference in sample means. We're going to subtract some assumed true difference. So we'll call this kind of capital D subscript 0. And then now here, I'm going to divide by the standard deviation of the statistic I'm interested in, which is the difference in sample means. And same thing we had for the confidence interval. That's just going to be, the square root of each group's variance over the sample size. Population, known population variance over the sample size. Or said differently, the variance on each sample mean. Yeah.
What is that stuff for?
What is what? Sorry.
What is all that stuff for up there? Like
Here?
what are they helping find?
Up here?
Yeah.
Yeah, so remember when we were doing hypothesis testing and we calculated this test statistic. And what that test statistic told us was the number of standard deviations away our sample mean was from this assumed true value. So this is another test statistic equation. It's just for a different statistic. So here we were converting sample means into the number of standard deviations away from the assumed true value. Even before, another one we looked at was, remember, we're still calculating a test statistic, but we could also do this for proportions. And there are all these test statistics are just telling us the number of standard deviation away our sample evidences from that assumed true value, whether or not that's our sample mean from the assumed true mean, sample proportion from the assumed true proportion, or the sample difference in means from the assumed true difference in those means. Does that kind of help? So thinking about this, like the reason why these test statistic equation works, maybe just to give a little more of like insight into to kind of make this a little more, help make this make a little more sense. Let's say I found a sample difference of, I don't know, 100, and I assumed the true difference is 50, right? So that's kind of like what's in my numerator. So I found this distance away from the assumed true value of 50. All I'm doing by dividing by the standard deviation, so let's say my standard deviation is 10, that's just going to convert whatever that difference was down to numbers of standards of deviations, right? So I was 50 away, the standard deviation was 10, that would be 5 standard deviations away, right? So we're always kind of keeping that same procedure. Take the sample statistic you are interested in, subtract the assumed true value of that statistic, divide by the standard deviation of that statistic. And what that's doing is it's converting that sample evidence into the number of standard deviations away from that assumed true value. Any other questions? That was good. Okay, so we can do different types of hypothesis testing, right? And what I'm often going to do, and I'll explain why in just a second, is we're actually going to make this a little bit easier. Before, where we had all these different assumed true population means, we're usually going to use 0 for the assumed true difference. And I think that'll make sense why in just a second. Now, it doesn't have to be 0. Any question I'll ask you on the exam, though, I'll use 0. There may be a couple in the next Connect assignment where they give you something other than 0. It doesn't really add a whole lot, other than you have to make sure you're subtracting it up there in your numerator. Okay. But most of the examples that we'll work through initially, we'll all be using 0. Kind of keep it simple. We'll kind of say the reason why 90% of the time that's what we're going to do anyways is use the assumed true difference of 0, but then maybe the other 10% of the time at the after we go through a couple examples, we might take a look and see, well, what if we didn't want 0? Probably won't be until Monday. But so we're going to have the exact same 3 types of tests, right? We're going to have the alternative and the null, where we're wanting to test for whether or not the difference is greater than 0 or greater than a specific value, less than 0, less than a certain value, or not equal to 0. Right? So we've got our same right, left, and our two-tailed tests, finding p-values, finding critical values, exactly the same as what we were doing before. That part literally doesn't change at all. The only part that changes is when we calculate our test statistic, we've got a slightly different equation now. It's still attempting, the test statistic is still telling me the same thing, but I'm calculating it slightly differently because I'm looking at a different statistic. So the reason why it's okay to use, I shouldn't say it's okay. The reason why I'm going to most often use this assumed true difference of 0 is, let's think about it this way, right? So if I say, let's say I start out and I want to find, is that difference greater than 0? Well, really what I'm saying is that difference in means greater than 0? Or if I rearrange this, what that's really saying is, does the first group have a larger mean than the second? I mean, that's the only way I get a positive difference. But a lot of times the way we'll say this is, what am I trying to test for? Does group 1 have a larger mean than group 2, right? Do econ majors make more from their starting salary than theater majors? Well, that's how we say it. But if I know that I'm trying to test for whether or not group 1 is greater than group 2, what I'm really saying there is then the difference can be greater than 0. You can imagine the opposite, right? If I wanted to say, okay, maybe I want to test for, is that difference less than 0? Well, what that's really saying is that difference less than 0? The only way that's true is if the second group has a larger mean. And then the final one, right? If we have we want to test to see, is there just a difference between these two groups, right? Is that difference anything other than zero? Well, what that's really saying is that difference not equal to zero, or does the mean from group one look, is it anything different than the mean from group two? So that's why zero is like a commonly used one, because like that's a lot of the things we're trying to find, right? I might want to test for whether or not country A has a larger, life expectancy or healthcare expenditures than country two. I might be interested if production process one produces a higher number of units in the same amount of time as production process two. Like all these things. Usually we aren't as concerned with, well, what's the gap in that difference? We just want to know, is one greater, is one less than the other, or are they different from each other? I'm trying to push this a little bit. We are going to use zero. And so we're often looking at, is one group having a larger mean than the other, lower than the other, or are they just different? What if I thought about, like, what if I did have, and here I'll use the econ theater majors as the example. So let's say that I wanted to try to test for whether or not the difference in their starting salaries was something other than 10,000. Actually, here, I'll do an easier one. Let's say I want to know, is that difference greater than 10,000? Right? Well, what I'm really saying there is the difference between my econ and theater majors starting salary. Not just do econ majors make more than theater majors, but if I rearrange this equation a little bit, what I'd really be saying is, do econ majors make more than 10,000, or sorry, make 10,000 more than theater majors starting salaries? So we might be interested in doing something like this in application. Maybe I am not just interested in, I think an example I sometimes give is like, so if I'm going into something, this is a good one. So in most industries, there's exceptions, but in most industries, we'll pick on physicians because I know that one for sure because I've seen the data, that male physicians' salaries are greater than female physicians' salaries, right? So that's what the data plays out. So if I'm interested in something like gender pay gaps and like I'm seeing it from my sample, a pretty large gap in between male and female average starting salaries for physicians, what I might do is say, okay, I know kind of going into this, that in this industry, historically, that difference is going to be positive. And it's not going to be a very interesting hypothesis test. I'll for sure be able to reject the null. But what would be harder to kind of find in the data is, well, not just is male starting salaries more than female, but is it 10,000 more, right? Or 20,000 more, right? Choosing some value. So in practice, we might want to use a different assumed true difference here. But for now, we'll just kind of keep using zero. And I think as we work through examples, you'll see like, this is going to be a common one that we want to use. So the steps, literally, we've seen this slide before. I copied and pasted it. It's the exact same. Steps don't change. Determine the null alternative. Figure out what level you're trying to testing at, right? Your alpha. Use that alpha and the type of test, left, right, or two-tailed test, to find your critical values. Plot those critical values in your rejection region. You can kind of draw those out and calculate your test statistic. If it falls in the rejection region, you can reject. If not, you fail to reject. Now, the other steps you could do is the p-value approach, which is don't find critical values, but use your test statistic to find your p-values. And then if that is less than alpha, we can reject. So we can still use either approach and just kind of have the critical value one up here to kind of show that there's no difference. I guess in a way there's a difference in that step 4, the steps are the same, but in step 4, I just have to use a slightly different equation to find my test statistic. Okay. We find p-values exactly the same way. So left tail test, right tail test, whatever my test statistic is, I want to find the area in the left tail for left tail test. That kind of represents my p-value. The right tail test, area to the right of my test statistic represents my p-value. Two-tailed test, I'll find the area in one of my tails. Remember that it would have been equally as likely to see evidence on the other side that went against that assumed true value. So I'll have to multiply by 2. Exactly the same as what we were doing before. And once again, if we're using that standard normal distribution, we'll find those same critical values over and over. And they're the same ones that we had for one population examples. So that was kind of a recap. Here, we already said, is our test statistic equation. let's try to kind of work through a problem here, right? So I've got that up here. We'll kind of try to work through these. So let's say I had this example where I got tropical storms and I want to know, have they increased over time, right? So I've got a newer time period and an older time period, and what? The sample mean, so for the newer time period, we've got 22 years, and we find on average every year there's 15.5 storms. We look at another 32, and we see on average every year there's 9.7 storms. We've got some known population variances somehow, like I said, a little bit hokey for now. We'll kind of move towards examples that are a little bit more practical. We're only at sample variances, but for now, we'll just assume someone gave us these population variances. So if I'm trying to identify the null alternative hypothesis here, I'm thinking about the difference, defining it as the newer time period. 1989, the other one ends in. Yeah. Difference between the newer time period and the older time period. Now, I want to know whether or not tropical storms have increased. How would I write this null alternative hypothesis? Yeah.
15.5 minus 9.7.
So that would be the sample evidence I found. If I just want to identify, no, you're correct, but if I just want to identify like what type of tail test do I have, I can think about it. If I wrote it out exactly how we said it here, I want to know whether or not tropical storms have increased, which would imply that the mean in 2011 is higher than 1989. Well, when I'm writing out my null alternative, I need to write this out in terms of the difference. Well, if I want the difference here, I would subtract this from both sides. This cancels, and what I'd be left with is that difference being greater than 0. Now, it might just intuitively make sense if I want to know if tropical storms have increased, and I'm thinking about taking the difference of the new time period minus the old. Well, the only way they've increased is if this difference is positive, right? Because if it was negative, that would imply that the older time period had higher tropical storm averages than the newer time period. So what we're trying to test for is this difference greater than 0? We assume the exact opposite is true for our null. So like I said, I think identifying the null alternative, especially when it's a one-tailed test, it's a little bit trickier here. You have to think about if I want to know if storms have increased, and I'm really thinking about that difference would be positive. And if I want to know if storms have decreased, I'd be thinking about that difference would be negative. So we've got what type of tail test here? Look at my alternative hypothesis. Yeah, I've got a greater than sign, so a right-tailed test. So the next step is what's the critical value for this right-tailed test where I've got, what is it, 5% significance level or 95% confidence level. So we just did this last class, so we're going to go through how we find these critical values a little bit more careful now. Remember, our critical value is essentially like a threshold number of standard deviations. So if I see sampled evidence that's more standard deviations away from the assumed true value than whatever this is, I'm okay rejecting. So it's like, here's my critical value, and for that right-tailed test, anything to the right of it, if I plot my test statistic and it's somewhere to the right of that, I'm okay rejecting. But how do I find that critical value? Well, it gives me alpha total in my tail, or in my tails, if I have two tails. Here we've got what? A right-tailed test, so just in one tail. So I want to find the z value, this kind of cutoff number of standard deviations that would give me that desired probability in the tail of 0.05. So how can I do this? So I hit exit there. I could use my z table. I could go find 0.05. Looks like I'm in between these two values. So negative 1.64, negative 1.65. Use the higher of the two. Negative 1.65, except for that's not quite right. So I just looked up alpha to find that corresponding z value. Why is that not quite the critical value for my right-tailed test over there? I subtract it from 1, right? But I think about what I just found. When I go to that table, I'm always looking up the area to the left. So when I looked up 0.05, I was finding the area to the left here. I had a right tail test, so my critical value won't be negative 1.65, it would be. Yeah, symmetric, so that same value for positive. So this is where we said, if I really wanted to technically be correct, when I go to that table, I really should be looking up an area of 0.95, or I can just remember if I just want to look up alpha, I'll find the exact value I need, it'll just be negative instead of positive for a right tail test. Now, another way I could have done this is use that last row, right, of the student T table to kind of cheat. So there, if I want 0.05 in my tail, go down to the very last row. I can actually even be a little more precise. I don't have to round to the second decimal. That critical value is actually going to be 1.645. Any questions over the process there? I know kind of the critical value stuff was still a little bit newer than what we did with the p-values. It's using kind of that inverse process where you know the area you want the tail, you need to find that corresponding z-value or number of standard deviations. So let's go back here. So we've got our critical value of 1.645. The next thing we need to do is calculate our test statistic. Now, one thing that's kind of nice when we're starting to look at these difference in sample mean problems is the sign of your test statistic, like, can kind of help you not make a really easy mistake. The sign of your test statistic has to be the sign of whatever that sample difference you found was. Because if I'm using an assumed true difference of 0, I can essentially just ignore that, right? Subtracting 0 doesn't change anything. If the denominator is a standard deviation, that always has to be, variances and standard deviations always have to be positive. So the sign of my test statistic will really just be, well, what's the sign of that difference you found in sample mean? So here, 15.5 minus 9.7, that's a positive difference. I should know that my test statistic has to be positive. So right away, I can move on D. From there, it's just a matter of getting my values plugged in. 15.5, 9.7. What? The variances were 25.5 and 7.8. And then I had, 22 and 32 years as kind of my sample sizes there. Just a matter of computation at that point. Now, just like with the confidence intervals, I would suggest calculate this first, this whole thing. That way you just have one value in the denominator there. But that you don't have to do that. Just kind of makes it a little bit easier to keep track of everything once you need a calculator. So I plug everything in, I should get a test statistic of about 4.9. So what that's saying is, based off the sample evidence, the change or the difference in the number of tropical storms is almost 5 standard deviations away from that assumed true difference of 0. So I found sample evidence that's pretty far away from that assumed true difference. In fact, it's so far away, if I plot it, right, against my critical values here, I'm very clearly in that rejection region. Now, this was kind of corresponding to alpha of 0.05, so with 95% confidence, I could reject this null. So if someone comes to me, I don't know, and they're like, yeah, this, tropical storms have actually decreased over the past 50 years, over these time periods. I could actually say I can reject that based off the sample evidence I'm looking at, the data I'm looking at. That actually goes against that assumed true difference of being less than or equal to 0. I found strong evidence that's in fact it's positive, right? That difference is positive. Questions on that? Couple things here. What if I wanted to be able to say this at the 99% confidence level? Why is it a little bit harder to be able to say that? Well, if I want to say this at the 99% confidence level, what's going to happen? What's the only thing that would change in this whole process? I no longer want an alpha of 0.05, but I want an alpha of 0.01. So my critical value would have to be a little bit larger, making it just a little bit less likely that my test statistics in the rejection. Now, in this case, my test statistic is so large that it probably won't matter if I actually look up that value in my table, it's not gonna be greater than 4.9. But maybe if I had a test statistic that was like 1.8, maybe then being able to say that a higher level of confidence, I couldn't actually reject the null there. Another thing I want to point out here, so we've got this critical value approach. We said we would reject at 95% level. What if I want to use the p-value approach here? We said we reject the p-value is less than alpha. Hopefully we're getting kind of used to thinking about z-values. What would the p-value be approximately here? What's the highest value in the z-table? 4. Right? So the area to the left of a test statistic of 4 is like 1, which means the area to the right is pretty much 0. If I'm seeing this extremely large test statistic, the probability I saw that, or anything to the right of it or above it for this right-tailed test, pretty much 0. Is that going to be less than 0.05? Sure is, so I make the same rejection decision. Questions on anything there? So that's how we work through a right-tailed test. I think. Oh, is that all I had here? I should have had the proportion stuff. I didn't have that up on there. Let me think about what I'm going to do here. I think I don't have those slides up on Canvas. So I think what I'll do, maybe we'll do a little bit of Excel today just so we can kind of line this up with as we're moving through it. So I think I put here. I'm going to take this right now and drop it in here. So 2 population stuff. I'll do the blank one first. Okay. So if you want to open up kind of that, where did it go? No, that's not 2 population HT blank. There it is, right? That's the kind of file that I'll be working with. So 2 population HT blank. Right. So I've got a couple different sheets in here. I think the one that I want to work with is over here, kind of that Midwest sheet. Okay. So I've got all these, a sample of universities and their enrollments. And then I have on another sheet, the South, right? If I go over here, I've got a data set where I've got a sample of Southern schools. Okay. So I'm going to start out here on the Southern one. I'm going to set this up. I've got all this in the file already. I'm going to give you these known population variances. This is a little bit hokey, but once again, we got to walk before we can run. So then what I'm going to do is, okay, I've got my Southern data here. I'm just going to find the mean for total undergraduate enrollment. Okay. Excuse me. Hit enter. I then want to find the mean for my Midwest enrollment. So one kind of trick that I don't think we've worked through yet is that, let's say I'm over here on my Midwest worksheet and I find the average total undergraduates. Once again, Control Shift, Command Shift on a Mac, hit the down arrow. And I'm going to find my sample size here as well using that count function. So I can see that I've got my sample mean and my sample size here on this other worksheet, but I need it to be on the same one as my Southern data. Right. So what I can do is, if I put an equal sign and then I click on this sheet, notice in the formula bar, it's letting me know it puts in, not only do we have row and column references, you can actually use sheet references. Now, if you're doing work on the same sheet, it just defaults to that sheet. But here I wanted to grab a value that's in cell M4 from this other worksheet, which was entitled Midwest. Now, a good way to get back to the original cell here is, once I click on that value that I want, just hit enter and it sends me back. And notice it grabbed that value, it put in that worksheet reference, and it grabbed the value that was on that worksheet in that cell M4, excuse me, which I selected. Okay. Now you could actually type this out. You have to use an exclamation point at the end of the name of the worksheet, but just clicking on the worksheet will automatically put it in there for you. Does that make sense? Any questions on that? So I don't know how many of you are like accounting majors, but I tried to forget as much accounting as I possibly can. But it's like, you've got what? Balance sheets, income statements, like all these different types. And a lot of the values are coming from, like, some of the values on your income statement might be coming from your balance sheet or vice versa. And so if you had them all in the same workbook, right, the same Excel file, you could actually like cross-reference these different worksheets using the values that you take from this statement to put it on the other one. Right? So it's pretty valuable to be able to reference these worksheets. Now here, I'm just going to copy this down because I had the data over here straight up and down. It's just going to update those cell references so that it's kind of going, instead of M4, to go down 2, it's going to be M6. And then I think I still need my sample size from my Southern School sample. Now I've got 2 sample means, 2 known population variances, 2 sample sizes. I could start to build confidence intervals, do hypothesis testing. Okay. So come down here. We're going to do confidence intervals exactly the same way that we would before, right? I need to find the number of standard deviations away I need to go to get alpha over 2 on either side. So usually I would use the inverse process, right? Look alpha over 2 up in the table, find that corresponding z value. Well, here, the equation we have for that is norm.s.inv. This is exactly the same way. I mean, it's identical to what we did for one population examples. I then tell it alpha divided by 2. Now, an issue is it kind of puts that negative. I kind of know the positive and negative already built into my confidence interval equation. So we said here we could just take the absolute value. Now I've got my 3 z values pretty quickly. Okay. Now at this point, it's just a matter of using Excel to be my calculator, right? Oh, sorry. So one thing I could do over here is, where do I have it? Here we go. Standard deviation for the difference in my sample means. Well, this is where, if I have that confidence interval equation written out, it's something like this, where I took the difference in my sample means, added and subtracted a certain number of standard deviations, and then divided by, right, that standard deviation of my sample means, or I could write the whole thing out. Now, what I would probably do is like break this down into the pieces, find that standard deviation of the difference in my sample means in this other cell here. So take the square root of group 1's population variance divided by, it's going to cover it up, but it's in M6. That sample size for that first group, add to that the population variance for group 2 divided by the sample size from group 2. All right, I'm just using Excel to be my calculator there and just breaking this down to steps so I don't make as many parentheses mistakes, perhaps. Right, but you could do this all in one, you could do this all in one cell to find the lower bound, just put in that equation if you wanted. I've just broken it down to steps here to make it a little bit easier. So once I go to calculate my lower bound, now all I need to do, take that, parenthesis, and did I find this as the difference in Midwest versus the South? So Midwest minus the South's average enrollment, right? That's what I'm basing my confidence interval around. I'll then subtract this many standard deviations. So I need to multiply that then by what is the value of the standard deviation. Okay. So all I've done there is use Excel to kind of be my calculator, kind of broke it down into pieces and used that norm.s.inv function to help me find the exact z value here. I don't have to use the table and approximate it. Also, something I'm noticing on these conference or on the last Excel, the Excel assignments, right? You're only going to get full credit if you use the formulas in Excel, right? You can't just, look up 1.96 from the table. You need to use that norm.s.inv function to receive full credit. Right? Otherwise, I would have just made it a regular assignment and not Excel. Right? I need you to use those Excel functions, okay? So from here, if I want to copy this down and do other confidence intervals, the only difference in my lower bound is that I'll be updating that z value. So everything else